The headline, when it finally reached the public, sounded like a joke. "We have detected trace amounts of magic at CERN." The sentence, written in this order, in print, in a serious science publication, was exactly the kind of sentence that any reasonable person would assume to be either clickbait or a stylistic flourish. And yet, in late 2024, that sentence was technically accurate. The word magic, as it turned out, was not a metaphor. It was the formal name, coined in 2005 by two theoretical physicists at Caltech, for a specific quantum information property that distinguishes a useful quantum computer from a useless one. The property had been detected by the ATLAS and CMS collaborations at the Large Hadron Collider in the spin correlations between top quarks and their antiparticles in proton-proton collisions at 13 trillion electron volts. The data had been on tape for nearly a decade. The formula needed to read it had existed since 2022. The calculation, when somebody finally ran it, took about an afternoon. So what was hiding in plain sight all that time? And if it's real, what does the term quantum magic really mean? Settle in. Subscribe so you can join the next journey and stay with us, because the answer is not what you would guess from the word alone. And the journey we're about to take together leads somewhere that almost nobody outside two narrow communities of specialists has heard about yet. Let's begin. Part 1. The Rule Nobody Wrote. In September of 2024, in a walled medieval seaport on the Atlantic coast of France, a particle physicist from London walked up to a podium and announced, in the calm tone of a man delivering a routine measurement, that the most violent collisions human beings have ever engineered were quietly producing magic. He did not put air quotes around the word. He did not soften it with a joke. He used it the way a chemist would use the word valence, or a geologist would use the word stratum. He said the word, and then he showed the math, and then he sat down. The room, which was filled with several hundred top quark specialists from CERN and Fermilab and the major universities of Europe and North America, applauded politely. A few of them took photographs of his slides. A handful of people in the back of the room understood immediately what he had just done. The rest would understand in the weeks that followed. This is one of those moments in physics that does not feel, at the time, like the kind of moment you remember. There were no headlines yet. There would be headlines, but those headlines would arrive months later, when the result had been picked up first by the in-house publication at CERN, and then by a few science journalists who actually read the conference proceedings, and then, finally, by the rest of the world. By the time the story reached most people, it would arrive in the form of a sentence that sounded like a joke. The sentence would be, more or less, "We have detected trace amounts of magic at CERN," and the people reading the sentence would assume, naturally and reasonably, that it was a joke. The word magic in 2024 was not a word that you expected to see in a serious physics paper, which is one of the reasons that the man at the podium in Saint-Malo did not say it with any particular drama. The drama was already built into the word. The word did not need any help. What he meant by it, though, is the thing the rest of this video is going to be about. And what we are going to do, slowly, with no rush, is walk together through what the word actually means. Because it is not a metaphor. It is not a literary flourish. It is not even an attempt by a physicist to make his field sound interesting to a lay audience, which would be unusual on its own, because most physicists do not try to do that. The word is the formal, mathematical, technical term that has been in use in a particular corner of quantum information theory for almost 20 years. It refers to a specific property of quantum states. The property has been measured in laboratories, in superconducting circuits, in trapped ions, in photonic chips. It has been the subject of dozens of peer-reviewed papers, and as of late 2024, it has also been measured in particle collisions at CERN, in the spin correlations between two of the heaviest particles in the known universe, the top quark and the top antiquark, born together from the energy of a proton-proton collision at 13 trillion electron volts. The reason this is the kind of moment you remember eventually is that it is the first time in the history of physics that a property invented to describe what makes a quantum computer faster than a classical one has been observed in a piece of nature that nobody designed for it. The man at the podium had not built a quantum computer. He had not engineered anything. He had taken data that the Atlas experiment had already taken and that the CMS experiment had already taken, and he had run a 6-line formula on it, and the formula returned a number that, in the language of his field, can only be described one way. The data showed magic. The universe, in a region smaller than an atomic nucleus, was producing the same property that engineers in Yorktown Heights and Mountain View and Beijing were spending billions of dollars trying to coax out of their cryogenic refrigerators. The universe had been producing it the whole time. The universe had been producing it since the first proton-proton collision in the first hot moments of the early cosmos. We had simply not known. If you find that hard to believe, you are in good company. Most physicists, when they first hear it, find it hard to believe. The result is the kind of result that sounds wrong twice. Once when you hear the word magic, and then again, in a deeper way, when you realize that the word is being used correctly, and that the correct usage implies something about reality that no one had been quite ready to say out loud. Because if the property that makes a quantum computer powerful is not a thing that engineers add to qubits, if it is instead a thing the universe was already doing by itself in the most fundamental interactions we have ever measured, then what does it mean to say that we are building quantum computers at all? Are we building them? Or are we, very slowly, learning to corner a feature of nature that has always been here, that has always been free, that has always been quietly running in the background of every interaction between every particle that has ever existed? These are the kinds of questions that the result raises. The man at the podium did not raise them himself. That is not what a physics conference is for. A physics conference is for the calm presentation of measurements, and the careful comparison of measurements to predictions. The implications come later. They come in the months and years after the conference, when other physicists read the paper, and when journalists try to translate it, and when philosophers of physics start writing essays about it, and when, eventually, the result settles into the public consciousness as one of those rare moments when a piece of mathematical theory and a piece of experimental data fit together so cleanly that you cannot tell anymore where the math ends and the world begins. We are still in the months and years after the conference. The implications are still landing, and what we are going to do in this video is sit with them, one at a time, and let them land slowly, the way the result itself has been landing in physics, not all at once, not with a thunderclap, but the way water finds the low places in a stone, the way a slow tide finds the line on a beach. So get comfortable. Settle in. The story we are about to walk through began in its most recent chapter in September of 2024 in a town called Saint-Malo on the coast of France. But its real beginning is much older than that. It goes back in one direction to the late 1940s and the first stirrings of what we now call quantum information theory. It goes back in another direction to the 1960s and the discovery that quarks exist at all. And it culminates, in the most recent 12 months, in a result that almost no one outside of two narrow communities of specialists has heard about, and that, if those specialists are right, will eventually be remembered as the moment that the boundary between quantum mechanics and quantum computing dissolved, and we discovered that the universe had been on the other side of it the whole time. Let me tell you what happened. Part 2. 2 papers in September. To understand what happened in Saint-Malo, we have to back up 2 months, because the result presented at the conference in September did not arrive in a vacuum. It arrived as a kind of second chapter, a quieter, stranger second chapter, to a result that had already been announced earlier that summer, and that had already begun, at that point, to ripple through the physics community in a way that most particle physics results do not. In late September of 2024, the journal Nature published a paper from the Atlas collaboration at CERN. Atlas is one of the 2 largest experiments at the Large Hadron Collider. It is named for the toroidal magnets that thread through its detector volume, a toroidal LHC apparatus. and it stands 46 metres long and 25 metres tall and weighs about 7,000 tonnes. It is a single instrument, but it is the size of a 6-storey building, and it sits at a point on the ring where 2 beams of protons cross each other 40 million times every second. The paper that Atlas published, in the issue of Nature dated September 12th, was titled Observation of Quantum Entanglement with Top Quarks at the Atlas Detector. It was the first paper in the entire history of high-energy physics to report a direct observation of quantum entanglement between 2 quarks. The number that the paper reported, the central result, was a single quantity that the Atlas team called the D-observable. The D-observable is a way of measuring how strongly the spin of a top quark is correlated with the spin of the antiquark it was born with. If D is greater than -1/3, the 2 spins are not entangled. They might be classically correlated, the way 2 coins struck from the same press might fall the same way more often than chance, but they are not quantum mechanically entangled in the Bell sense, in the way that has been associated with quantum weirdness since the 1930s. If D is less than -1/3, the 2 spins are entangled. They have to be. There is no other mathematical way to produce a D value below that threshold from any classical theory of correlation. Atlas measured D equals -0.537, with a statistical uncertainty of about 0.002 and a systematic uncertainty of about 0.019. The measurement was made in a narrow window of the invariant mass of the top-antitop pair, specifically between 340 and 380 giga-electron-volts, which is the energy range just above the threshold where it becomes physically possible to create a top-antitop pair at all. The value, comfortably below -1/3, was more than 5 standard deviations away from any scenario in which the spins were not entangled. In the language of particle physics, 5 sigma is the threshold for discovery. Atlas had crossed it. The first observation of entanglement between quarks was now part of the published scientific record. It was also, by a wide margin, the highest energy observation of quantum entanglement in any system in the entire history of physics. The previous record, set by photonic experiments and superconducting circuits, had been measured at energies of a few electron volts. The Atlas measurement was made at energies 13 orders of magnitude higher, 10 trillion times more energetic. Quantum mechanics, which had been seen most often as a feature of very small and very cold systems, was now confirmed to be alive and well at the highest energies humans have ever created. The CMS experiment, the other major detector at the LHC, sitting on the opposite side of the ring from Atlas. Its acronym stands for the Compact Muon Solenoid, and despite the word compact in its name, it is in fact heavier than the Eiffel Tower, published its own version of the same result earlier that year. CMS used a slightly different invariant mass window, between 345 and 400 giga-electron volts, and a slightly older data set from 2016, with a total of 36.3 inverse femtobars of integrated luminosity. In English, that means CMS analysed about 3 trillion proton-proton collisions to make the measurement. CMS measured D equals -0.480, with uncertainty of +0.026 and -0.029, also comfortably below -1/3, also confirming entanglement between the top and anti-top spins. 2 independent detectors, 2 independent data sets, 2 independent analyses, 2 independent conclusions. The result was solid. Entanglement at the highest energies humans have ever observed was, as of 2024, no longer a matter of theory or speculation. It was simply a measurement. But the CMS team did something more. They extended their analysis into a regime called the boosted regime. The boosted regime is the part of the data where the top quark and the anti-top are produced flying apart very quickly, with high momentum in opposite directions. In this regime, the 2 particles are spatially separated by the time they decay by a distance that is large enough, and they decay quickly enough, that no signal travelling at the speed of light could possibly have connected them. They are, in the technical language of relativity, space-like separated. If anything happened to one of them after they were produced, that information could not have reached the other before both of them had ceased to exist. They lived and died as two independent objects in two independent regions of space-time that could not communicate. And in that regime, CMS measured the D observable. The number, again, came in below -1/3. The spins were entangled. The correlations between them violated the Bell inequality. And the violation was happening between two particles that, in the strictest possible relativistic sense, had no way to be in contact with each other at the moment they were measured. This is, in technical terms, a Bell test. It is the same kind of test that won the 2022 Nobel Prize in Physics for Alain Aspect, John Clauser, and Anton Zeilinger, three physicists who, over the course of 40 years, had progressively closed every conceivable loophole in the experimental demonstration that quantum mechanics is genuinely non-local. By 2015, with the loophole-free tabletop Bell test done by Ronald Hansen's group in Delft, by Anton Zeilinger's group in Vienna, by the National Institute of Standards and Technology in Colorado, the case was closed at the tabletop level. Quantum mechanics was, definitively, not a theory that could be reproduced by any local hidden variable model. Reality, at the quantum level, was not the kind of reality that classical physics had always assumed. The CMS-boosted regime result extended that same conclusion from photons at room temperature to top quarks at 13 trillion electron volts. It pulled the rug, in other words, out from under any remaining hope that maybe quantum mechanics' strange non-local correlations were a feature only of very small, very gentle, very controlled tabletop systems. They are not. They are a feature of the universe at its most extreme. They are present in the most energetic, most fundamental, most violent particle collisions that humans have ever produced. The same quantum mechanics, the same non-locality, the same Bell-violating correlations, just 13 orders of magnitude higher. If you have ever heard the phrase that quantum mechanics is weird, this is the largest scale and most direct confirmation of that weirdness ever produced. And it was published in the summer and fall of 2024 with relatively little fanfare in a couple of high-impact journals and a handful of conference proceedings. The headlines, when they appeared, said things like, "Physicists observe entanglement at record energy." The headlines did not yet say anything about magic. That part was still coming. That part was what the man at the podium in Saint-Malo would deliver 2 months after the Atlas paper appeared in Nature. And here is the thing to keep in your mind as we move forward. The word is not a metaphor. It is going to keep being not a metaphor. Every time in the rest of this story that we use the word magic, we are using it the way Chris White used it from the podium. We're using it the way it has been used in the quantum information theory literature for nearly 20 years. We're using it as the formal name for a precise, measurable, mathematically defined property of quantum states. A property that is, as we are about to see, the very specific thing that separates a quantum computer that is genuinely faster than a classical one from a quantum computer that is just an expensive replica. The word is not a metaphor. Hold on to that, because we are about to see why. Part 3. The second lens. So, 2 months after the Atlas paper hit Nature, in a conference room in Saint-Malo, France, on the afternoon of either the 25th or 26th of September, the conference programme lists it as part of the second-to-last session. A physicist named Chris White, from Queen Mary University of London, walked up to the podium and presented a paper whose title, on the conference programme, read simply, "The Magic of Top Quarks." His co-author, Martin White, from the University of Adelaide in Australia, was either not present or watching by video link, depending on which member of the conference staff you ask. The two of them are not related despite sharing a last name. They had been collaborating for several years on the intersection between quantum information theory and high-energy physics. They had published an earlier paper together in June of that same year, titled The Magic of Entangled Top Quarks. The September paper at the TOP 2024 conference was the follow-up. The conference itself was the 17th International Workshop on Top Quark Physics. It had been held in Saint-Malo, a a fortified medieval seaport on the Brittany coast of France, from the 22nd to the 27th of September. The town is famous for its granite ramparts, which the rising tide of the English Channel washes up to twice a day, and for being the birthplace of Jacques Cartier, the French explorer who, in 1534, claimed Canada for France. The conference itself was held in a modern conference centre inside the old town walls. The talks were given in French and English, often in the same talk. The coffee breaks were held on a balcony that overlooked the harbour. From inside the conference centre, when the windows were open, you could hear the gulls. What Chris White presented in those 20 minutes at the podium was the following. He had taken the same spin-density matrix, the same mathematical object that Atlas and CMS had been measuring in order to detect entanglement, and he had run a different calculation on it. He had not changed any of the data. He had not used any new measurements. He had used exactly the values that Atlas and CMS had already published, and he had fed them through a formula that came not from particle physics, but from quantum information theory. The formula was called the stabilizer Rényi entropy. It had been introduced in a 2022 paper in Physical Review Letters by 3 Italian quantum information theorists named Lorenzo Leone, Salvatore Oliviero, and Alyosha Hammer. And what the formula did was compute, from any given quantum state, a number that quantified how much of a specific resource that state contained. The resource had a name. The name was magic. What he found, when he ran the formula on the top-anti-top spin density matrix, was that the number was not 0. It was not even close to 0. Across most of the kinematic regions where the LHC produces top pairs, the number was substantial. The top-anti-top system was magic-rich. It was a system that contained large amounts of the specific resource that, in quantum computing, separates a useful quantum computer from a useless one. And this is the part that he said calmly, without flourish, in the same tone he had used for the rest of the talk. This was the first time in the history of high-energy physics that any property other than entanglement from the quantum information toolkit had been measured at a particle collider. The LHC, which had been operating since 2008, which had produced the discovery of the Higgs boson in 2012, which had run for more than a decade of physics with an array of measurements that had filled hundreds of papers, was now suddenly also a place where magic could be observed. The same data, the same machine, the same particles, a different lens. The room, as I mentioned earlier, applauded politely. The audience was, after all, a room full of top quark physicists. They had spent their careers measuring the properties of this particular particle. They knew the spin density matrix. They knew the Fano coefficients, which is the technical name for the entries in that matrix. They had seen these numbers 100 times. They had not, until that moment, seen them fed through a magic formula. And they had not realized, many of them anyway, a few of them had been working on this kind of thing themselves, that the data they had been collecting for over a decade contained in plain sight the signature of a quantum information property that had been the subject of intense study in a completely different field. That is the kind of moment that physicists describe later, in interviews, by saying things like, "We should have seen it earlier." That is also the kind of moment that, retrospectively, is recognized as one of the small turning points in the history of a field, the moment when a fence between two communities of researchers comes down, and the people on either side of the fence look at each other and realize that they had been studying the same thing all along. The talk did not make the cover of any newspaper. It did not make the cover of any magazine. The proceedings of the conference were eventually published several months later as part of the SciPost Physics Proceedings series, a peer-reviewed open-access journal that publishes proceedings from physics conferences. The archive number of the paper, for anyone who wants to look it up, is 24/12.07479. It is 4 pages long. It contains, in those 4 pages, the calculation in full, the figure showing where magic peaks in the kinematic plane of top pair production, the formula that does the work, and a list of references. It is the kind of paper that, if you were not looking for it, you would not find. It is also the kind of paper that, once you have read it and understood what it actually says, you cannot unsee. The June paper, the predecessor, The Magic of Entangled Top Quarks, is longer, 18 pages, posted on the arXiv as 2406.07321. That paper does the heavier theoretical work. It establishes the framework. It shows that the relationship between entanglement and magic is more interesting than you might guess. The two properties are independent. A state can have a lot of entanglement and very little magic, or a lot of magic and very little entanglement, or, as the LHC seems to produce, a moderate amount of both. The September conference paper is the cleaner, shorter, more accessible version. If you only have time to read one of them, you read the September paper. If you want the full derivation, you read the June paper. Together they form the foundation of what has, in the year and change since, become a small but growing subfield, the intersection of quantum information theory and high-energy collider physics. And the thing that makes the result strange in the way that you cannot quite shake off no matter how much you sit with it, is that the data was already there. The Atlas measurement of the spin density matrix had been on tape for years. The CMS measurement had been on tape for nearly a decade. The Fano coefficients had been published in dozens of papers, in dozens of presentations, in technical notes filed at the CERN document server. The magic formula had existed since 2022. The calculation took, according to one of the authors, an afternoon plus a couple of weeks to be sure I hadn't made a stupid mistake. The barrier between the data and the result was not a technical barrier. It was a barrier between two fields that, until very recently, did not talk to each other very much. The barrier was language. The barrier was the conventions of which conferences you attended and which journals you read. The barrier was, in some sense, the social structure of physics, which has always, for reasons that mostly come down to the size of modern science and the difficulty of staying current in any one specialty, divided the world into a few hundred sub-communities that only occasionally pollinate one another. And when one of those acts of pollination happens, when somebody who knows the language of one community walks across the room and starts talking to the people on the other side, every once in a while the result is that a piece of mathematics that has been sitting on a shelf for a few years suddenly turns into a new way of seeing the world. That is what happened in Saint-Malo. That is what the man at the podium was, calmly and without flourish, telling everyone in the room. The applause was polite. The implications would take a while to settle. We are going to walk through them now, slowly, one at a time. But first we have to back up. We have to go back to where the word magic came from in the first place. Because if you are going to follow this story all the way through, you need to understand why a property of quantum states is called by a name that, on the face of it, sounds like a joke. Part 4. Where the word came from. The year was 2005. The place was the California Institute of Technology in Pasadena, where two physicists were finishing a paper that would slowly, over the next 2 decades, reshape how the world thought about quantum computers. The first of the two was Sergei Bravyi, a Russian-born theoretical physicist who had come to Caltech as a postdoctoral researcher a few years earlier. The second was Alexei Kitaev, a Russian-born physicist who had been a senior researcher at Caltech for almost a decade by that point, and who was, by 2005, already one of the most respected figures in the small but rapidly growing field of quantum computing theory. Kitaev had, in 1997, invented something called the toric code, which would later become the foundation of nearly every serious proposal for building a fault-tolerant quantum computer. He had also, in 2003, written a paper proposing a class of particles called non-abelian anyons that, if they existed, could be used to build a quantum computer that was naturally immune to most of the noise problems that plague conventional designs. He was the kind of physicist that other physicists listened to very carefully when he spoke. The paper that he and Bravyi finished in 2005 was titled Universal Quantum Computation with Ideal Clifford Gates and Noisy Ancillas. It was published in Physical Review A, Volume 71, paper number 022316. On the surface, the paper was a technical contribution to the theory of quantum error correction, specifically the question of how you might build a working quantum computer out of imperfect parts. The problem with imperfect parts in quantum computing is that quantum information is extraordinarily fragile. The slightest disturbance from the environment can scramble it. If you build a quantum computer out of physical qubits that have, say, a 1 in 10,000 chance of an error on any given operation, then by the time you've done a few thousand operations, the answer is garbage. The only way to build a useful quantum computer is to use error-correcting codes, clever arrangements of many physical qubits that, working together, can hold the information of a single logical qubit in such a way that the logical information is protected from any single physical error. This is roughly the same idea as the error-correcting codes that protect data on a hard drive, or the redundancy that lets a satellite signal punch through static. But the quantum version is harder because you cannot simply copy a quantum state. There is a theorem, the no-cloning theorem proven by William Wouters and Wojciech Zurek in 1982, that says quantum information cannot be perfectly duplicated. So the error correction has to be done differently. It has to be done by spreading the information across many qubits in a way that any individual qubit state contains, by itself, nothing useful, and yet the collection of them all together still encodes the logical information you want to protect. This is the world that Bravee and Kitaev were working in. Their paper was, on the surface, about how to build the logical operations, the gates, of a fault-tolerant quantum computer. They focused on a particular set of gates known as the Clifford gates. The Clifford gates are a specific group of quantum operations that have very pleasant mathematical properties. There are only a few of them, and they include things called the Hadamard gate, which takes a qubit pointing in one direction and flips it to a superposition of two directions, the phase gate, which adds a quantum mechanical phase to part of a state, and the controlled NOT gate, or CNOT, which flips one qubit conditional on the value of another. These three gates, used together in different combinations, can generate the entire Clifford group. The Clifford group is a finite, well-understood set of operations. They're easy to error correct. They are the natural choice if you're trying to build a robust quantum computer. But there is a problem. The Clifford gates, by themselves, are not enough. A quantum computer that can only do Clifford operations is, it turns out, not actually a quantum computer in the useful sense. It can do quantum things. It can create superposition. It can create entanglement. It can do measurements that look quantum in every way. But it cannot do anything that a classical computer cannot also do, given the same amount of time. There is a theorem that proves this. The theorem is called the Gottesman-Nil theorem, named for Daniel Gottesman and Manny Nil, who proved different versions of it in 1997 and 1998. The Gottesman-Nil theorem says, roughly, that any quantum computation that uses only Clifford gates, starting from any of a certain class of input states, the so-called stabilizer states, can be simulated efficiently on a classical computer. Not just simulated efficiently. The classical simulation takes about as long as the quantum computation. There is no speed up. There is no quantum advantage. The whole point of building a quantum computer, the reason anyone is spending billions of dollars on this, is to do things faster than a classical computer can. And a Clifford-only quantum computer cannot do that. It is, in a real sense, an expensive emulator of a classical machine. So what is missing? What is the missing ingredient that you have to add to a Clifford-only quantum computer in order to make it actually faster than a classical one? This is the question that Bravee and Kitaev set out to answer. Their answer was both simple and strange. They proved that all you need is one more gate. You need a single, specific, non-Clifford gate. Any non-Clifford gate at all. And once you have it, you can build a universal quantum computer. The Clifford gates plus any one non-Clifford gate are enough. The universe of possible quantum operations becomes accessible. You can compute anything any quantum computer can, in principle, compute. The problem is that the non-Clifford gate is the hard one. The non-Clifford gates are difficult to implement in any real physical system in a way that preserves the error-correcting structure. They are the bottleneck. The reason quantum computers are so expensive to build is not the Clifford gates. those are relatively easy. It is the one non-Clifford gate that you have to add to make the whole thing work. And here is where Bravyi and Kitaev had their key insight. Instead of trying to build the non-Clifford gate directly, they proposed something different. They proposed that you could prepare off to the side a special quantum state, a state that, on its own, was outside the family of stabilizer states. You could prepare this state imperfectly. You could prepare many copies of it. You could then use the Clifford gates, which you have already built, to distill those imperfect copies into a smaller number of much purer copies. And then, when you needed to do a non-Clifford operation in your quantum computation, you could consume one of these purified states as a kind of fuel, and the consumption would, by the rules of quantum mechanics, effectively perform the non-Clifford operation for you. The state was the ingredient. The Clifford gates plus the state equaled the universal quantum computer. They needed a name for these special states, and the name they chose, half as a joke, half because the field genuinely lacked a better word, was magic. They called them magic states. The non-Clifford operations that the magic states enabled were called magic gates. The procedure for purifying noisy magic states into clean ones was called magic state distillation, and the whole framework, the idea that you build a quantum computer by combining easy Clifford gates with a separate supply of magic states, became known as the Bravyi-Kitaev framework. It is by far the most influential framework in fault-tolerant quantum computing. Almost every serious proposal for a real quantum computer that anyone has built or proposed in the last 20 years uses some version of it. IBM's fault-tolerant roadmap uses it. Google's roadmap uses it. The various academic and industrial proposals for topological quantum computers, photonic quantum computers, trapped ion quantum computers, all of them, in one way or another, ultimately depend on having a reliable source of magic states. The Bravyi-Kitaev paper has been cited, as of the time of this video, more than 2,000 times. It is one of the most cited papers in quantum computing, and the word, despite being half a joke when it was coined, has stuck. It has stuck in a way that the people who coined it did not entirely expect. In 2005, Bravyi and Kitaev did not think they were naming a new fundamental property of nature. They thought they were naming a useful technical construct, a state that you could build in a lab with effort to make your quantum computer work. They were engineers. They were solving an engineering problem. The fact that, almost 20 years later, the word magic would turn up in the title of a particle physics conference talk, a talk about a quantity that has been measured at CERN in two of the most highly engineered scientific instruments in the world, in collisions between fundamental particles whose existence Bravyi and Kitaev had nothing to do with predicting, would have struck them, in 2005, as a strange and unexpected outcome. The word was supposed to be a piece of engineering slang. It was not supposed to be a name for something that the universe was already producing on its own. But the way the word found its second life, the way it travelled from the engineering of quantum computers to the spin correlations of top quarks, is the story of what came in the years after Bravyi and Kitaev's paper. And what came was, slowly, the realization that magic, the engineering concept, was actually a deep, fundamental, mathematically rigorous property of all quantum states, not just states you tried to build in a lab, all of them, and that property could be measured in principle in any system you cared to look at. The barrier was finding the right formula, and that formula would not arrive until 2022, when 3 physicists in Italy would write a paper in Physical Review Letters that introduced the stabilizer Rényi entropy, and that gave the rest of physics a tool to look for magic anywhere it might be hiding. And the place it would turn out to be hiding, 2 years after that paper appeared, was inside protons, in the heart of every proton-proton collision at the Large Hadron Collider. Part 5. The Room with a Ceiling. Before we can go any further, we need to spend a little time on the Gottesman-Nil theorem itself, because the Gottesman-Nil theorem is the reason magic exists as a concept at all. Without the Gottesman-Nil theorem, there would be no need to single out one class of quantum operations from another. There would be no reason to think that any quantum state was particularly special. All quantum states would look, on first glance, like the kind of thing that classical computers could not handle. The Gottesman-Nil theorem is the thing that changed that, and it is one of those mathematical results that, once you have understood it, you cannot stop seeing the implications of. Daniel Gottesman, the man whose name leads the theorem, was a PhD student at Caltech in the mid-1990s. His advisor was John Preskill, one of the founding figures of the modern field of quantum computing. Gottesman's thesis, completed in 1997, was titled Stabilizer Codes and Quantum Error Correction. In it, he introduced a piece of mathematical machinery called the stabilizer formalism. The stabilizer formalism is a way of describing certain quantum states without having to write out their full wave functions. Instead of writing out the wave function, which can have an exponential number of terms, and which is the reason why simulating quantum systems on a classical computer is generally so hard, you describe the state by listing the operators that leave the state unchanged. These operators are called the stabilizers of the state. If you know the stabilizers, you know the state, and the stabilizers are a much, much more compact way of writing the information down. Instead of needing an exponential amount of memory, you need only a polynomial amount. This was a striking observation in its own right. It meant that there was a class of quantum states, not all of them, but a meaningful subclass, that you could describe compactly on a classical computer. Gottesman called these states stabilizer states. The set of operations that mapped stabilizer states to stabilizer states, the operations that preserved the structure, were exactly the Clifford gates we talked about a moment ago, the Hadamard, the phase, the Synod, and the measurement operations in the standard basis. These were exactly the operations that, when applied to a stabilizer state, produced another stabilizer state. The next year, in 1998, Gottesman, together with Manny Nil, a physicist at the National Institute of Standards and Technology in Colorado, proved the theorem that now bears their names. The theorem says, in essence, any quantum computation that uses only Clifford gates and starts from a stabilizer state can be simulated efficiently on a classical computer. The simulation runs in polynomial time, not exponential time, polynomial time, which means, for any computational problem that this kind of restricted quantum computer can solve, a classical computer can solve the same problem in roughly the same amount of time. There is no quantum advantage, there is no exponential speed-up. The whole machinery of quantum mechanics, when restricted to Clifford operations on stabilizer states, is, computationally, just classical mechanics in a fancy disguise. This was a very strange result, because stabilizer states can include some of the most quantum-looking states anyone had ever imagined. They include the Bell pairs, the maximally entangled 2-qubit states that are at the heart of the EPR paradox and Bell's theorem. They include the GHZ states, the 3-qubit entangled states that John Bell famously called the most surprising states in quantum mechanics. They include cluster states, which are the workhorses of the measurement-based quantum computing. All of these states are entangled. Many of them are maximally entangled. They are all things that, from any naive perspective, you would expect to be useful for quantum computation, and yet the Gottesman-Nil theorem says, no, they are not. Even with all the entanglement in the world, a quantum computer restricted to Clifford operations is no faster than a classical one. So entanglement by itself is not the source of quantum advantage. Superposition is not the source of quantum advantage. The thing that makes a quantum computer faster than a classical computer is something more specific, something more delicate, something that, until 2005, did not have a name. Bravyi and Kitaev gave it one. They called it magic, and they showed, in their 2005 paper, that magic was exactly what was needed to break out of the stabilizer state cage and access the full computational power of quantum mechanics. I want you to picture a room. Imagine that the room is enormous. Imagine that the walls of the room stretch out as far as you can see, that the ceiling is so high that you cannot quite make it out, and that the room is filled, floor to ceiling, with all of the quantum states that a classical computer can efficiently simulate. These are the stabilizer states. They fill the room. There are many of them. They include the entangled ones, the not entangled ones, the superpositions, the basis states, the GHZ states, the Bell pairs, everything that the Clifford operations can reach. The room is vast. From the inside, looking around, you might be forgiven for thinking that it contains everything. You might think that quantum mechanics in its entirety fits inside this room, but it does not. Because if you walk to the edge of the room and you push on the wall, you find that it is a wall. The room has boundaries, and just outside the room, no more than a half step beyond any of its walls, there are quantum states that the classical simulation cannot keep up with. These states do not look, on first inspection, particularly different from the ones inside the room. They are not more entangled. They are not in some bigger Hilbert space. They are not the kind of state that anyone would point to and say, that is obviously special. They are just, in some quiet mathematical way, not stabilizer states. They are non-stabilizer states, and the property that makes them non-stabilizer states, the property of being outside the room, is what Bravyi and Kitaev called magic. The magic states are the ones just outside the door. And here is the strange thing. Once you have a single state from outside the room, plus the operations you have inside the room, you can reach every other state in the universe of quantum states. The single outside state used as a kind of resource lets you build any quantum computation you want. The room becomes, in a sense, infinite. The walls vanish. You can compute anything. But you need that one state. You cannot do without it. And the state by itself sitting outside the room is what carries the actual quantum advantage. The state is the magic. This is a strange picture, and I want to let it sit for a moment, because it goes against the way that quantum mechanics is usually taught. We're usually told that the strange and powerful things about quantum mechanics are superposition and entanglement. That is what every popular book on quantum computing tells you. That is what every undergraduate textbook on quantum mechanics tells you. Superposition and entanglement, the two great features, the two engines of the quantum revolution. But the Gottesman-Nil theorem says, very clearly, those are not the engines. Those things alone are not enough. There is a third thing. The third thing is harder to picture, harder to name, harder to talk about. It is the property of being outside the stabilizer room. It is the property of being a state that cannot be reached by Clifford gates from a stabilizer input. It is the property that Bravyi and Kitaev called magic. And it is the thing that does the actual work, in a real quantum computer, of making the quantum computer faster than the classical one. For nearly 20 years after Bravyi and Kitaev coined the term, the discussion of magic stayed mostly inside the world of quantum computing engineers. The people who were thinking about it were the people building quantum hardware. They were the ones who had to actually distill magic states out of noisy raw inputs, the ones who had to design error-correcting codes that could survive the destructive measurements that magic state consumption required. Magic was their problem. It was an engineering problem. The rest of physics, by and large, did not pay attention. Particle physicists were busy with the Standard Model. Astrophysicists were busy with dark matter and the cosmic microwave background. Condensed matter physicists were busy with high-temperature superconductors and topological insulators. Nobody outside of the small quantum computing community had any particular reason to think about magic, because nobody outside that community was building quantum computers, and the formal definition of magic, the technical machinery that would let you measure it in an arbitrary quantum state, did not exist yet. That changed in 2022. In that year, the three Italian physicists I mentioned earlier, Lorenzo Leone and Salvatore Oliviero, both of whom were graduate students at the time at the Università degli Studi di Napoli Federico II, and Alyosha Hammer, their advisor, published a paper in Physical Review Letters that gave the field for the first time a clean, computable, universally applicable measure of magic. They called it the stabilizer Rényi entropy. The paper appeared in volume 128, issue number 5, with the article number 050402. It was 9 pages of dense mathematics. It introduced a formula that, given any quantum state, any quantum state anywhere in any system would return a number. The number would be 0 if the state was a stabilizer state. The number would be positive otherwise. The larger the number, the more magic the state contained. The formula was, for the first time, a thermometer for non-stabilizerness. You could point it at any quantum system and read off how much magic that system contained. And the moment you have a thermometer for a previously unmeasured property, every system in the universe becomes a candidate for being measured. The thermometer goes into condensed matter systems. It goes into trapped ion experiments. It goes into superconducting qubits. It goes into photonic chips. It goes eventually into the spin correlations of top quarks at the Large Hadron Collider. The room with the ceiling, in other words, was no longer something you could only describe in the abstract. You could, starting in 2022, measure where any given state sat relative to the walls of that room. And once you can measure something, the next step is always the same. You point the instrument at whatever is interesting, and you see what you find. 2 years later, in 2024, Chris White and Martin White pointed the instrument at top quarks, and they found magic. Part 6. The 6-line calculation. Let me try to give you the formula, not because I am going to ask you to do algebra in your head, but because it is important to see how simple it actually is. The thing about the stabilizer Rényi entropy is that once you have it written down, it does not look like the kind of formula that you would expect to be the answer to one of the deepest questions in modern physics. It looks like the kind of formula that you would find on a homework problem in an upper division quantum mechanics class. It is short, it is symmetric, it uses ingredients that any physics graduate student would recognize. It hides its depth completely. That is one of the things that, when you finally see the formula written down, makes the whole result feel slightly unreal, because you cannot quite believe that something so straightforward could have been waiting, in plain sight this whole time, to be turned on data that everyone already had. The formula is this. You take a quantum state. You pick a number, call it Q, and the number has to be greater than or equal to 2. The simplest case, and the one that Chris White and Martin White use for top quarks, is Q equals 2. You take all the operators called Pauli strings. The Pauli strings are tensor products of the 3 Pauli matrices plus the identity. For 2 qubits, which is what a top-anti-top pair effectively is, there are exactly 4 times 4 or 16 possible Pauli strings. For more qubits, the number grows exponentially, 4 to the power of the number of qubits. But for 2 qubits, you have just 16 operators to deal with. That is a small number. That is the kind of number you can write out on a single sheet of paper. For each of those 16 Pauli strings, you compute the expectation value of that operator in the state you're studying. The expectation value in quantum mechanics is a number that tells you what the average outcome would be if you measured that observable repeatedly on copies of the state. For a stabilizer state, the expectation values of the 16 Pauli strings all take very particular values. They're either +1 or -1 or 0, with exactly 4 of them being non-zero and the rest being 0. That is the technical definition of a stabilizer state in this language. For a non-stabilizer state, a magic state, the expectation values do not take those clean values. They spread out. They take values between 0 and 1 in various proportions. The pattern is messier. The pattern carries more information. The stabilizer Rényi entropy takes that pattern and reduces it to a single number. You take each of the 16 expectation values, you raise them all to the power of 2q, which for q equals 2 means raising them to the 4th power. You add them all up, you divide by some normalization, and then you take the logarithm, base 2, of the whole thing, and what comes out at the other end is a number. The number is 0 if the state is a stabilizer state. The number is positive otherwise. The larger the number, the more magic the state has. That is it. That is the formula. It is half a page of arithmetic. It uses only the things, the spin density matrix, the expectation values of Pauli operators. that experimental particle physicists have been measuring routinely for 50 years. It needs nothing exotic. It needs no new measurements. It needs no new theory. It needs only the existing data, fed through the formula and a calculator. Chris White and Martin White's 2024 paper at the top 2024 conference is, in essence, an exercise in this kind of calculation. They took the spin density matrix that Atlas and CMS had measured for top-anti-top pairs. They wrote down the 16 Pauli string expectation values. They raised them to the fourth power. They added them up. They took the logarithm. And what came out was a number that was not zero. The number, in fact, was not just non-zero. It was substantial. Across most of the kinematic phase space, that is, across most of the combinations of invariant mass and scattering angle, where the LHC produces top pairs, the magic was clearly non-zero, and in some regions it reached values that, in the language of quantum information theory, would be considered significant. The top-anti-top system was, in their measurement, a magic-rich system. It was producing the resource that quantum computers need in order to be faster than classical computers. It was producing it in nature, by itself, without anyone trying to make it do so. I want to dwell on this point for a moment, because it is the central conceptual move of the whole result, and it is easy to slide past it without noticing what is being said. When you build a quantum computer in a laboratory, you have to make the magic. You have to engineer it. You have to take a system of qubits that, in their default state, are in stabilizer states, which is what happens, more or less by default, when you cool a quantum system down to its ground state, and you have to actively manipulate them with carefully tuned laser pulses or microwave pulses, or whatever your control mechanism is, to push them out of the stabilizer space and into the magic space. It is hard. It is, in fact, the hardest part of building a useful quantum computer. The Bravyi-Kitaev framework that we talked about a moment ago, the whole machinery of magic state distillation, the 5 input states to 1 output state purification protocol, the 5-qubit error-correcting code, that whole machinery exists for one reason. It exists because making magic states is hard, and the magic states you make are always noisy, and the only way to use them in a real quantum computer is to distill them down to clean ones. The entire engineering challenge of building a quantum computer, in some sense, comes down to the engineering challenge of reliably producing magic. But nature, when you set up a proton-proton collision at 13 trillion electron volts, produces magic for free. It does it without any control system. It does it without any cryogenic refrigerator. It does it without any laser pulses or microwave pulses. The collision happens. The top quark and the antitop are born together out of the available energy. Their spins are correlated in whatever way the laws of quantum chromodynamics require. And quantum chromodynamics, the theory of the strong force that governs how quarks behave, is a theory that has been written down since the early 1970s, has been refined and confirmed in tens of thousands of measurements, has won 3 Nobel Prizes along the way, and does not, anywhere in its mathematical statement, contain any reference at all to magic stabilizer states or the Bravyi-Kitaev framework. And yet, when you carry out the calculation that the theory requires you to carry out, what comes out at the end is a spin density matrix whose stabilizer Rényi entropy is not 0. The theory was always going to give that answer. The theory had been giving that answer in every spin density matrix it had ever been used to compute since the 1970s. No one had noticed. The question that pulled the answer out had not yet been asked. This is the moment in the story when the strange feeling really starts to land, because we tend to assume, when we talk about quantum computers, that we are doing something fundamentally new. We are building, with great effort, machines that do things the universe itself does not do, that exploit features of quantum mechanics that nature itself does not exploit. The whole rhetoric of the quantum computing industry is built around this assumption. We are pushing the frontier. We are reaching into a regime that nature has never been in. We are accessing capabilities that have not existed in the history of the universe. But the calculation that Chris White and Martin White ran says, no, that is not what is happening. The universe is already in that regime. The universe is already exploiting those features. The top-anti-top pair at the moment of its production in a proton-proton collision is already a magic-rich quantum state. We have not been adding magic to the universe by building quantum computers. We have been, painfully and at enormous expense, trying to corner and harness a property of nature that has always been here, that has always been free, that has always been quietly active in every interaction between every particle in the cosmos that anyone has ever managed to measure. The quantum computer engineers in this picture are not pioneers reaching into a new regime. They are inhabitants of the regime trying to make it usable for our purposes. That is the conceptual shift. That is the thing that the six-line calculation does. It does not change the math of quantum mechanics. It does not change the data of any experiment. It changes how we think about what we are doing when we measure quantum systems. It changes what we think the universe is doing, all around us, all the time, whether we are watching or not. Hold on to the picture of the room with the ceiling. We're going to come back to it. Because in a moment, we're going to look at where the magic peaks, where in the kinematic plane of top-pair production, the LHC produces the most of it, and where it produces less. And that map, when we have drawn it, is going to start telling us something else. It is going to start telling us not just that the universe produces magic, but where the universe produces it. And the answer is going to surprise us. The answer is going to surprise us almost as much as the existence of the result itself surprised the physicists who first saw it. We are still in the foothills. Part 7. The Map of Magic. Imagine for a moment a plot. You have two axes. On the horizontal axis is the invariant mass of the top-anti-top pair. That is the total energy of the two particles, measured in the rest frame where their combined momentum is 0. The smallest value this can take is about 346 giga-electron volts, which is just twice the mass of the top quark, the energy you need, by Einstein's relation between mass and energy, to cool two top quarks out of the vacuum at rest. The largest value in principle is unbounded, but in practice the data runs out somewhere around 2000 giga-electron volts, because the LHC simply does not produce many top pairs at energies that high. So the horizontal axis runs from 346 to 2000 giga-electron volts. On the vertical axis is the scattering angle, the angle, measured in the rest frame of the top pair, between the direction the top quark goes and the direction of the incoming proton beam. This angle runs from 0, which means the top quark goes straight along the beam direction, to 180 degrees, which means it goes the opposite way. The most interesting region is in the middle, around 90 degrees, where the top quark goes off at right angles to the beam. If you take this two-dimensional plot, and at every point on it you compute the stabilizer Renyi entropy of the top-anti-top spin density matrix, you get a map. The map has hills and valleys. The hills are the places where the magic is high. The valleys are the places where the magic is low. And the structure of the map is, as I said a moment ago, surprising. Because the magic is not maximized where you might naively expect. It is not maximized at the threshold, at 346 giga-electron volts, where the top quarks are produced at rest, and where the entanglement is also strongest. There, the magic is actually low. It is also not maximized at very high energies, where the top quarks are produced moving very fast with high momentum. There, again, the magic is low. The magic is maximized in the intermediate regions, neither at threshold nor at high energy, but somewhere in between, where the top quarks are produced with moderate momentum and where the angular distribution has a certain non-trivial structure. Why is this? The reason, when you trace it back through the math, turns out to be a consequence of a fact that we have already mentioned but not yet emphasized. Stabilizer states include both the most boring quantum states, the ones with no correlations at all, and the most interesting ones, the maximally entangled ones. The room with the ceiling, the one we have been picturing, is big enough to hold the maximally entangled states inside it. They are inside the room. They are not magic. Even though they are entangled, they are not magic. And so, at the threshold of top pair production, where the spin density matrix is dominated by a single, well-defined, highly entangled configuration, that configuration is a stabilizer state, or close to one. The magic, accordingly, is small, and at very high energies, where the spin density matrix is dominated by a different highly structured configuration, a so-called separable state, where the spins of the top and the antitop are independent of each other. Again, that is a stabilizer state. The magic is small there too. The places where the magic is large are the places where the spin density matrix is, in some sense, in between, where it is neither maximally entangled nor maximally separable, where the spin correlations are complicated, mixed, partially entangled, partially not. These are the kinematic regions where the state is, technically speaking, the most generic, where it is the least clean, where it does not fit cleanly into any of the special categories that stabilizer state theory carves out. And it is precisely these generic, in-between, messy states that turn out by the formal definition to have the most magic. This is a strange and beautiful observation, because it means that the magic of the universe is not concentrated in the most striking, photogenic configurations of matter. It is concentrated in the in-between places. It is concentrated in the states that, to a naive observer, would look ordinary. The flashy states, the maximally entangled bell pairs, the perfectly separable independent qubits, are, in this measure, magic poor. They sit inside the room. The states that look unremarkable, the ones with the kind of correlation structure that you would barely notice unless you knew what you were looking for, those are the ones that sit just outside the door. Those are the magic-rich ones. Those are the ones that, if you could harness them, could fuel a quantum computer. And the place where this is most clearly visible in the LHC data is in the difference between the two main ways that top pairs are produced. At the LHC, top pairs come from two distinct initial states. About 10% of them come from quark-antiquark annihilation, what physicists call the QQ bar channel, in which one proton supplies a quark and the other supplies an antiquark, and they meet head-on to produce the top pair. About 90% of them come from gluon-gluon fusion, what physicists call the GG channel, in which two gluons, which are the force-carrying particles of the strong nuclear force, the things that bind quarks together inside protons, merge into the top pair. Both channels produce top pairs. Both channels have well-defined predictions in the standard model, but the two channels produce top pairs with different spin correlation structures, and accordingly, when Chris White and Martin White ran their calculations separately on each channel, they found different magic maps. The QQ bar channel produces magic in a different pattern from the GGG channel. The two maps overlap in some places, differ in others, and combine, when you sum them with appropriate weights, into the overall magic distribution that the LHC actually produces. Combining channels, it turns out, generally increases the magic, because the combined state is more mixed than either individual state, and the more mixed a state is, the more complicated its Pauli spectrum, and the more magic it tends to have. This is a subtle point, but it is a useful one to keep in mind. The LHC, when it produces top pairs from both channels at once, produces a state that has more magic than it would if it produced them from only one channel. Nature, when it sums over the available production mechanisms, ends up making more magic than any individual mechanism would make. What this map tells us, taken as a whole, is that magic is not an exotic property of nature. It is not a fragile, rare, easily disturbed property that you only find in carefully prepared laboratory states. It is a robust feature of the most generic quantum systems. It shows up whenever the system is complicated enough to have a non-trivial correlation structure. It shows up in particle collisions, it shows up in atomic physics, it shows up in condensed matter, it almost certainly shows up in chemistry, it probably shows up in biology. We have not yet measured all of these, but the map of magic in top pair production, and the way it peaks in the generic in-between regions of the kinematic plane is a strong hint that magic is everywhere in nature, in roughly the same way that entropy is everywhere in nature. It is a feature of complexity. It is what you find when you look at any system that has enough structure to support correlations. And this means that the question that the LHC measurement raises is not, is magic real? That question is now answered. Magic is real. The question is, what else has it been hiding in? What other systems in our existing experimental data contain measurable magic that we have not yet measured, because no one has bothered to compute the stabilizer Renyi entropy of the data? The answer, almost certainly, is many of them. There are probably dozens of experimental measurements in dozens of subfields of physics and chemistry where the data is already in hand, the spin density matrix or its analog is already known, and the only thing missing is for someone to take an afternoon, sit down with the formula, and run the calculation. Each one of those calculations would be a small extension of the LHC result. Each one would push the frontier of our understanding of where in nature the resource that powers quantum advantage is hiding. This is, in some sense, what is most exciting about the result. Not the magic of top quarks specifically, although that is striking enough, but the larger implication that the toolkit of quantum information theory, which has been developed over the last 30 years for entirely engineering reasons, can now be applied as a measurement framework across the rest of physics. We have, in 2024, gained a new instrument. Not a new telescope, not a new collider, not a new accelerator, but a new mathematical instrument, a new way of reading the existing data. And the first thing we have pointed that instrument at, the top quark, has shown us that the instrument works, that the readings are meaningful, that the universe was producing the thing we were measuring all along. Where else does this go? That is what the rest of physics is now starting to think about. And the answers, when they come, are going to keep arriving slowly over the next several years. We are, all of us, watching a young story unfold. And the next part of the story, the part we're going to walk through now, is going to take us deeper. Because the map of magic in top pair production turns out not to be just a map. It is, on a closer look, a set of clues. Clues that point at 4 different, distinct, unresolved questions in fundamental physics. We're going to look at all 4. Part 8. 4 anomalies. There are, when you look closely at the LHC magic measurement, 4 distinct things that are unexpected about it. We have already touched on some of them, but it is worth now walking through all 4 together, because they form a kind of pattern, and the pattern is what gives the result its real philosophical weight. The first anomaly is the basic existence of the result. Nothing in the standard model of particle physics, when you write the theory down on paper, says anything about magic. The standard model is a theory of forces and particles. It tells you what kinds of particles there are: quarks, leptons, force carriers, the Higgs boson, and what kinds of interactions they have. It is written in the language of quantum field theory, which is itself a very particular mathematical framework that uses creation operators, annihilation operators, propagators, and Feynman diagrams. The framework does not, anywhere in its statement, mention the words stabilizer, Clifford, magic, non-stabilizerness, or stabilizer Renyi entropy. The framework is, in this sense, completely silent on the question of whether top pairs produced in the framework should have non-zero magic. There is no theorem that says they should. There is no theorem that says they shouldn't. The question simply did not arise, and yet, when you carry out the calculation that the standard model dictates, when you work out the spin density matrix of top pairs in proton-proton collisions, using the well-established machinery of perturbative quantum chromodynamics, plus the established electro-weak interactions, what comes out, at the end, is a state with non-zero magic. The standard model, without saying anything explicit about it, predicts magic. The prediction is a side effect of the underlying physics. It is what physicists sometimes call an emergent property, a property that arises from the equations even though the equations were not written down with that property in mind. And then, when you compare the prediction to the data, which is what Chris White and Martin White did, the prediction is borne out. The data and the prediction agree. The universe is doing the thing that the equations imply it should do, even though no one had ever previously asked the equations to imply anything about magic. The second anomaly is the kinematic distribution. We touched on this already, but I want to come back to it. The magic peaks in the in-between, generic regions of the kinematic plane, not at threshold, where the entanglement is strongest, not at high energies, where the production is most boosted, in the middle, where the state is mixed, partially entangled, partially not. This is, on first inspection, almost the opposite of what you might expect. You might have expected that more entanglement implies more quantum advantage and therefore more magic. But that turns out to be wrong. Entanglement and magic are two independent quantum resources. They are correlated in the sense that you usually need both for a quantum computer to be useful, but they are not the same thing. A maximally entangled state can have zero magic. A high magic state can have only modest entanglement. The two resources live in different mathematical dimensions, and they peak in different parts of the kinematic plane. The LHC produces a sweet spot, a region where both resources are simultaneously present, neither maximized, but both non-zero. And that sweet spot is, technically speaking, the most computationally interesting configuration that the LHC produces. The third anomaly is the channel dependence. The QQ bar channel and the GG channel produce different magic maps. This sounds, at first, like a minor technical detail, but its implications are significant. It means that magic is not a generic feature of any particle pair that emerges from any reaction. It is specifically sensitive to the dynamics of how the particle pair is produced. Different production mechanisms produce different magic landscapes. This means that magic, like entanglement before it, can be used as an experimental probe of the underlying physics, not just a property to be measured, but a tool for measuring other things. If you wanted to test, for example, whether there is some new physics beyond the standard model that affects top pair production in a particular way, some new heavy particle that mediates between the initial quarks or gluons and the final tops, you could now check whether that new physics modifies the magic map in a measurable way. If it does, magic becomes a discovery channel. It becomes a new way of looking for things that the standard model does not predict. And this is in fact one of the most concrete short-term promises of the result. The next several years of LHC running, plus the high luminosity LHC upgrade that is scheduled to start around 2029, will collect roughly 10 times more data than the LHC has collected to date. With that data, the magic measurement will become much more precise. The kinematic maps will be more finely resolved. The comparison between the QQ bar and GG channels will be sharper, and any anomaly, any place where the data deviates from the standard model prediction, will be a hint of new physics. Magic, in this sense, becomes one more tool in the standard search for physics beyond the standard model. It joins the search for supersymmetry, the search for dark matter candidates, the search for hidden sector particles, the search for extra dimensions, and the search for any deviation from the predictions of the canonical theory. It is a new way of looking, and new ways of looking in physics are how you find new things. The fourth anomaly is the boosted regime. We have already mentioned this, but I want to come back to it with the magic framing now in place. The CMS measurement of entanglement in the boosted regime, where the two top quarks fly apart so fast that no signal could communicate between them before they decayed, is, in the strict relativistic sense, a Bell test. It is a demonstration that the spin correlations between the two particles cannot be explained by any local hidden variable theory. They are genuinely non-local. They are genuinely quantum. The result extends the conclusions of the loophole-free tabletop Bell tests of 2015, the experiments of Ronald Hansen's group in Delft, of Anton Zielinger's group in Vienna, of the National Institute of Standards and Technology in Colorado to energies 13 orders of magnitude higher. The same conclusion, the same non-locality, the same Bell violation, just at TeV scales instead of electron-volt scales. Now, when you add the magic measurement to the picture, what you have, in the boosted regime, is something even stranger. You have two particles that are space-like separated. You have spin correlations between them that violate the Bell inequality. And you have, on top of that, magic, non-stabilizerness, the resource that fuels quantum computational advantage, present in the spin density matrix. The state is both Bell non-local and computationally magic. It is, in essence, the kind of state that a quantum computer engineer would dream about producing. And it is being produced naturally by the universe, in a region of space-time where no information can flow between the two particles, in collisions that happen 40 million times every second in a tunnel 100 meters under the French-Swiss border. I want to pause here, because this is the place where the result taken in full starts to become hard to hold in your mind. Each of the four anomalies on its own is striking. Together they paint a picture that is, I think, genuinely difficult to fully process. The picture is this. The universe, in its most violent, most fundamental, most energetic interactions, is producing, for free, without any engineering, without any human intervention, quantum states that have the precise mathematical signature of the most prized, most expensive, most carefully engineered states that quantum computer scientists are trying to build. The universe is doing it spontaneously, at high energy, in collisions whose mechanics are governed by the laws of quantum chromodynamics, which were written down in the early 1970s without anyone having any idea that they would, 50 years later, turn out to be predicting the production of quantum computational fuel. The universe was already doing this. The universe has always been doing this. We just did not know. This is the existential weight of the result. The thing that engineers in Yorktown Heights and Mountain View and Beijing spend billions of dollars trying to coax out of cryogenic refrigerators is not new. It is not unique to human technology. It is not a frontier we have reached. It is, in the formal mathematical sense, the same resource that has been quietly present in every proton-proton collision in the history of the universe, and in every analogous high-energy interaction, in every analogous high-energy event since the moment the universe was hot enough to produce hadrons. We are not pioneers, we are very late guests. The universe was here before we arrived, and the universe was, by the strictest technical definition, already doing the thing. Let that sit. Because we are about to look at what this means for the next 20 years of quantum computing. The honest engineering question, the question of whether the LHC can become, in any practical sense, a source of magic states for real quantum computers, is the next thing we have to think about. And the answer, when we get to it, is going to be no. But the journey to that no is, in some ways, more interesting than the no itself. Before we go there, though, I want to add one more layer to the four anomalies picture, because it is the layer that, in some ways, ties the others together. The four anomalies are not four separate surprises. They are, on closer inspection, four faces of the same underlying surprise. The underlying surprise is that the universe, at energies 13 orders of magnitude beyond any laboratory in which Bell tests have ever been conducted, in collisions that are governed by an entirely different theory from the one that defines magic in a regime that no one designed for any of this, the universe, in all of those conditions, is doing the same thing. The same quantum mechanics, the same non-local correlations, the same non-stabilizer states, the same magic, the fact that the four anomalies all line up, that they all agree, that the prediction from quantum information theory matches the data from particle physics, is the strongest single piece of evidence we have that quantum mechanics is not a description of small, gentle, isolated systems. Quantum mechanics is the description of nature, the same description, at every scale, in every interaction, from the most controlled laboratory state to the most violent particle collision the universe has ever permitted. There is one set of rules. The rules apply everywhere, and the rules contain magic, built in at the foundation. That is where we go now. Part 9. Can we harness it? Let me ask the engineering question directly, because it is the question that anyone who has followed the story this far has probably already started to ask. If the universe is producing magic states in proton-proton collisions, and if magic states are the rare, expensive resource that limits the development of useful quantum computers, then could we, in some far future sense with sufficient engineering, use the LHC as a source of magic states for a quantum computer? Could CERN, with its 27-kilometre ring and its 40 million collisions per second crossing rate, become a kind of natural magic state factory, producing the resource humanity needs to build the next generation of quantum machines? The answer, unfortunately, is no. And the reasons are worth walking through, not because the engineering is interesting in itself, but because the reasons illuminate something important about the result. The first reason is that top quarks decay very, very quickly. The lifetime of a top quark is about 5 times 10 to the minus 25th seconds. To give you a sense of how short that is, a top quark lives for less time than it would take for a light signal to traverse the diameter of a single hydrogen atom. Less than 1/10 of the time it takes for a single proton in the nucleus to move through one of its quantum mechanical oscillations. Less, in some sense, than the time it takes the universe to do almost anything. The top quark exists, in any meaningful sense, for an interval that is shorter than essentially any other timescale in physics. It is the only quark that decays before it has time to bind into a hadron. That is, the only quark we ever observe as something close to a free particle. The only quark whose spin information is not immediately scrambled by the strong force binding it to other quarks. This is what makes the spin density matrix measurable in the first place. The brevity of the top quark's life is what gives us access to its spin. If it lived even 100 times longer, the spin information would be lost to the strong force before the decay could carry it to the detector. The brevity is, paradoxically, what makes the measurement possible. But the same brevity is what makes the magic unusable as a quantum computational resource. You cannot store a quantum state that lasts for 10 to the minus 25th seconds. You cannot route it. You cannot connect it to anything. By the time any apparatus you might design has even begun to register the existence of the top quark is gone. The decay products, the W bosons that the top emits, the bottom quarks that those decay into, the leptons and the jets that emerge at the end, carry away the spin information in the statistical pattern of their angular distribution, which is what ATLAS and CMS actually measure. But the magic state itself, in its purest form, lives for an interval too short to interact with anything human-engineered. This is the first reason the LHC cannot be a magic factory. The magic is transient. It happens, and then it is gone. It does not stick around. The second reason is the production rate. Even though the LHC produces a lot of top pairs by the standards of particle physics, about 1 million per year per detector, in the high luminosity era, that is, in the context of building a working quantum computer, a vanishingly small number. A real quantum computer with computational advantage over a classical one needs, in current estimates, somewhere between thousands and millions of magic states per second, sustained, for the duration of any non-trivial calculation. The LHC produces top pairs at a rate of less than 1 per second, on average. You could not run a quantum algorithm on the LHC's magic supply, even if you somehow solved the storage problem. There simply are not enough top quarks being made. So the LHC is not a magic factory. It cannot be one. Whatever the long-term future of quantum computing turns out to be, it will not run on top quarks. It will run on the kinds of qubits that engineers have been working on for the last 2 decades. Superconducting circuits, trapped ions, photonic chips, neutral atoms, possibly topological qubits if they ever work. The LHC is not in that picture, but that is not in fact the end of the story. because there is a second engineering question that the LHC magic result does open up, and that question is not, can we use LHC magic as a quantum computational resource, but rather, can we use the LHC as a precision testbed for the theory of magic? And the answer to that question is yes. Here is what I mean. The stabilizer Rényi entropy is a mathematical object. It is defined formally. It has theoretical properties, invariances, additivity rules, behavior under various operations that have been worked out by Leon and Oliviero and Hammer and their collaborators in a series of papers over the last few years. But like all mathematical objects in physics, the stabilizer Rényi entropy is only as good as the experimental systems that can verify its predictions. Before the LHC measurement, the theory of magic had been tested in only a relatively small number of contexts, mostly in superconducting qubit experiments, and mostly in highly controlled, highly engineered states that researchers had specifically designed to test the theory. The LHC measurement is different. It is a test of the theory of magic in a system that no one designed for that purpose, that has its own independent dynamics governed by an entirely separate physical theory, quantum chromodynamics, and where the predictions of the magic theory and the predictions of the underlying physical theory have to agree, or the theory of magic is wrong. The two theories meet in the LHC data. They have to be consistent, and the fact that they are consistent, that the magic measurement comes out exactly where Chris White and Martin White predicted it would, with the kinematic structure they predicted, with the channel dependence they predicted, is a strong piece of experimental support for the entire theoretical framework of stabilizer Rényi entropy. This is not the same as harnessing magic for a quantum computer, but it is a way that the LHC is now contributing to the field of quantum information theory. The contribution is bidirectional. The quantum information theorists provided a new lens to look at LHC data. The LHC data, in turn, validates the theoretical framework that the quantum information theorists have been developing. The dialogue between the two fields is now real, in a way that it was not before 2024. Now I want you to picture something. I want you to picture the LHC at night. The ring is 27 kilometers around. It is buried about 100 meters below the French and Swiss countryside near the city of Geneva. At any given moment, when the machine is running, there are about 10,000 billion protons circulating in each of the two beams that race around the ring in opposite directions, packed into bunches that are about 100 billion protons each, with about 2,800 bunches per beam. The bunches cross at 4 points around the ring in 4 separate detector caverns: Atlas at point 1, Alice at point 2, CMS at point 5, LHCb at point 8. Each crossing produces on average 20 or 30 proton-proton collisions, depending on the running conditions. Each collision produces a spray of particles. Most of the particles are debris, pions, kaons, photons, electrons, the ordinary aftermath of high-energy interactions. A small fraction of collisions produce something rarer. A vanishingly small fraction produce a top-anti-top pair. The pair is born in an interval of time too short to picture. The two particles emerge, back-to-back in some frame, their spins quantum mechanically correlated in a way that the laws of quantum chromodynamics dictate. For an interval of about 5 times 10 to the minus 25th seconds, an interval too brief for any conceivable mechanical clock to register, the pair exists as a coherent quantum state. Their spin density matrix in that moment has the structure that Chris White and Martin White calculated. The stabilizer Rényi entropy is, in that moment, not zero. The pair is magic. It is, in the technical sense, doing what a qubit pair in a quantum computer would have to do, by careful engineering, in order to be useful for any computational task that beats classical computation. And then the top quark decays. It emits a W boson, which decays further. The bottom quark recoils. The whole apparatus of the strong interaction takes over. The pair, as a coherent quantum object, ceases to exist. By the time any of this has reached the silicon trackers and the calorimeters and the muon chambers of the Atlas or CMS detector, let alone by the time any of it has been recorded in the data acquisition system, let alone by the time any of it has been reconstructed in software, let alone by the time it has been published in a paper, the original magic state has been gone for thousands of trillions of times its own lifetime. It was there. It is gone. It will be back in the same building in approximately 25 nanoseconds when the next bunch crossing happens, and it will be gone again before anyone has noticed. This is the rhythm of the universe's magic production. It is happening right now while you are listening to this. The LHC has been off since late last year, in a planned maintenance period before the start of Run 3's second extended period in 2026. But there are similar processes happening in lower energy particle colliders elsewhere, in Brookhaven, in Hamburg, in Tsukuba, and there are top quarks being produced in cosmic ray interactions in the upper atmosphere, in the cores of distant active galactic nuclei, in the ancient particle showers that fill the universe with high-energy debris from every supernova that has ever exploded anywhere in the visible cosmos. The universe is producing magic, constantly, everywhere. We just cannot store it. We cannot use it. We can only, with our instruments, measure that it is happening, and in some sense, that is enough. It is enough to know. Part 10. The geometric reading. Now I want to take you, for a few minutes, into a more speculative region. I want to mark this clearly. What I am about to describe is not data. It is not measurement. It is not a result. It is a conjecture, a careful, well-developed, mathematically rigorous conjecture, but a conjecture that some theoretical physicists have been quietly developing for the last few years, and that the LHC magic result has, slightly, made more interesting than it was before. The conjecture is that magic might be, in some deep sense, dual to geometry. That measuring magic might be, indirectly, measuring the shape of an emergent higher dimensional space-time. I want you to hear this with the right level of caution. I am not telling you that this is true. I am telling you that it is a possibility that some people are taking seriously, and that the LHC result is consistent with it. Whether it is actually true is a question that may not be answered in our lifetimes. To explain it, I have to back up and tell you about a piece of physics that, even by the standards of modern theoretical physics, is strange. It is called the holographic principle, or sometimes the AD-CFT correspondence, and it was proposed in 1997 by an Argentine-born theoretical physicist named Juan Maldacena, who was at Harvard at the time and who is now at the Institute for Advanced Study in Princeton. The Maldacena paper, The Large N Limit of Superconformal Field Theories and Supergravity, published in Advances in Theoretical and Mathematical Physics in 1998, is one of the most cited papers in all of physics, more than 20,000 citations as of the time of this video, and it proposed an idea so surprising that, for years after it appeared, many physicists considered it more of a thought experiment than a serious physical proposal. The idea has, since then, become one of the cornerstones of modern theoretical physics, but it remains, in its broadest reading, a conjecture rather than a proven theorem. The idea is this. Maldacena showed that there are certain quantum field theories, specifically certain conformally invariant quantum field theories living in a flat four-dimensional space-time that are, in a precise mathematical sense, equivalent to certain theories of gravity living in a five-dimensional curved space-time called anti-de Sitter space. The equivalence is not a metaphor. It is not an analogy. It is, in the technical sense, an isomorphism. Every quantity you can compute on the quantum field theory side has a corresponding quantity you can compute on the gravity side, and the two answers always agree. The two theories are, by every test that has ever been done on them, the same theory, expressed in two completely different mathematical languages. This is strange because the two theories live in different numbers of dimensions. The quantum field theory lives in 4 dimensions. The gravity theory lives in 5. The fact that they are equivalent is what gives the principle its name. The holographic principle says that, In some sense, a four-dimensional quantum field theory contains all the information of a five-dimensional gravitational theory, in the same way that a two-dimensional hologram, in a clever optical setup, can encode all the information of a three-dimensional image. The dimensionality is, in some sense, an illusion. The information is the same, you can read it either way. Now, here is where this becomes relevant to magic. There has been, over the last few years, a quiet program of research, in papers by various combinations of authors, the relevant archive numbers going back to about 2023, investigating the question of what, on the gravity side of the holographic correspondence, magic on the field theory side corresponds to. In other words, if the quantum information property called magic is present in a particular state of the quantum field theory, what does that translate to in the dual gravitational picture? What is the geometric meaning of magic? The conjecture in its broad form is that magic in the field theory corresponds to something like the wormhole structure, or the entanglement geometry of the bulk gravitational theory. There are technical proposals, the magic of bulk boundary correspondence, the magic as volume conjecture, various other proposals that I will not try to summarize in any detail because they are not yet settled. What is interesting in the broad picture is that magic, the quantum information property that engineers care about, may turn out to be a probe of the geometric structure of an emergent higher dimensional spacetime. And if that conjecture is right, then measuring magic in the spin density matrix of top quarks at the LHC is, in some indirect sense, probing the geometry of a higher dimensional spacetime that is dual to the quantum chromodynamics of the proton-proton collision. I want to be careful here. This is speculation. The holographic principle, as a general framework, is well established for certain special quantum field theories, specifically the so-called maximally supersymmetric Yang-Mills theory in 4 dimensions. But its extension to the actual quantum chromodynamics of the real world is a different and harder question. There are approximate, partial, sometimes useful versions of holography for QCD-like theories. There are no exact ones. So the chain of reasoning that takes you from the LHC measured magic in top pairs to the LHC as probing higher dimensional geometry is a long chain, and it has several links that have not been definitively forged. It is, at this point, a thread of suggestive ideas rather than a proven conclusion. But it is a thread that is worth knowing about, because if it turns out in the next 10 or 20 years that this picture is right, that magic is the field-theoretic shadow of geometric features in an emergent bulk, then the LHC measurement will be remembered as the moment when quantum information theory and quantum gravity, the two great unsolved frontiers of modern physics, started to speak to each other through experimental data rather than through pure theory. Quantum gravity has, for most of its history as a research field, been blocked by the lack of experimental data. The energies at which quantum gravity becomes important, the Planck scale, around 10 to the 19th giga-electron volts, are 16 orders of magnitude higher than what the LHC can probe directly. There is no obvious way to test quantum gravity in the laboratory. This has been the field's central frustration since at least the 1970s. But if the holographic conjecture is right, then quantum gravity is not just lurking at the Planck scale. It is also, in some sense, encoded in the quantum field theory that we already can probe, and the lens that lets you read the quantum gravity information out of the quantum field theory data is, in this picture, the toolkit of quantum information theory: entanglement, magic, contextuality, and the other resources. The LHC magic measurement, in this view, is one of the first experimental data points in what would eventually become a much larger program of trying to read out the geometric structure of the universe from quantum information signatures in particle physics data. Whether this picture turns out to be the right one is, I will say again, an open question. There are physicists who think it is. There are physicists who think it is not. The honest version of the answer in 2026 is that we do not yet know. But the result that Chris White and Martin White presented in Saint Malo in September of 2024 is, regardless of which interpretation eventually wins, the kind of result that the holographic program had been waiting for. It is a quantum information measurement made in a high-energy physics experiment that the two communities can now discuss together. It is a bridge. The bridge may eventually lead to deeper waters, or it may turn out to be a charming detour. Either way, it has been built, and it is now there. I am going to leave this thread here, because I do not want to oversell it. The main story of the video is not the holographic conjecture. The main story is the magic measurement itself, and what that measurement implies about the nature of the universe. The holographic possibility is a footnote, an interesting footnote, possibly an important footnote, but a footnote. The fact that the universe is producing magic in top-pair production is, by itself, enough to fill the rest of this video with implications. We do not need to go all the way to wormholes and emergent geometry to find things to think about. We have enough, sitting right here, in the spin density matrix that Atlas and CMS have already measured, to keep us busy for the rest of our lives. But the thread is there. The possibility is there. The room with the ceiling, the one we have been picturing, may turn out to have walls that are not what they look like from the inside. The walls may turn out to be, in some deep mathematical sense that no one has yet entirely worked out, the surface of a higher dimensional object that we cannot see from where we stand. The doorway out of the room may not be a doorway. It may be a window, opening on a geometry that exists in a number of dimensions different from the one we live in. That is the possibility. We are not going to settle it tonight. We are going to come back in the next part to the more concrete and more grounded picture. The picture of the universe as a quantum computer that was always running, that has always been faster than any classical machine, and that we are very slowly learning to read. Part 11. The universe was already here. I want you to imagine for a moment that you're standing in an empty field at night. Not anywhere in particular. Just a quiet field somewhere on a small planet in an unremarkable arm of an ordinary spiral galaxy, in the middle of nowhere especially. The sky above you is full of stars. There are about 3,000 stars visible to your naked eye, which is approximately 1/10 of 1% of the stars in the observable universe. The air around you contains roughly 2.5 times 10 to the 25th molecules per cubic meter, each of them performing the small quantum dances of vibration and rotation and interaction that define the physical chemistry of an ordinary atmosphere. The ground beneath your feet is made of atoms whose nuclei are bound together by the strong force. That same strong force that, in the much more extreme conditions of a proton-proton collision at the LHC, produces magic-rich top-anti-top pairs at a rate of about 1 per second. There is no LHC here, there is no detector. There are just atoms and molecules and photons and the quiet quantum interactions that build the fabric of an ordinary night. And every single one of those interactions, every quantum interaction in the air around you, in the ground beneath you, in the photons from the sun that left its surface 8 minutes ago and reached your eyes tonight after bouncing off a leaf or the moon or your own breath. Every one of those interactions involves quantum states with non-zero stabilizer Renyi entropy. Every one of them contains magic. The universe is producing magic by the second, by the nanosecond, by every interval of time too small to put a name to, in every cubic millimeter of space, on this planet, on every other planet, in every star, in every galaxy, in every region of intergalactic space, where two photons have ever interacted with each other in any way. The universe has been doing this since the first hot moments after the Big Bang. The universe will continue doing it until the last black hole evaporates, perhaps 10 to the 100th years from now. Magic is not a feature of human technology. Magic is, in the formal mathematical sense, a feature of the universe itself. I want you to hold this picture in your mind for a moment, because it is the picture that the LHC result actually delivers. The result is not just about top quarks. The result is about the universe. The universe is a system of quantum interactions, and those quantum interactions in any sufficiently generic regime produce non-stabilizer states. The non-stabilizer states are the magic-bearing ones. The magic is the resource, and the resource is not concentrated in any particular place. It is everywhere. It is in the proton-proton collisions at the LHC. It is in the atoms of the air around you. It is in the spin states of the electrons in the rock beneath your feet. It is in the photons from your own neurons firing in the moment that you are processing what I am saying. It is, by the strict mathematical definition, present in essentially every quantum interaction in the universe. This is what the result actually tells us. And it tells us something even more specific than that. It tells us that the universe is, in a precise, computable, measurable sense, a quantum system that classical computers cannot keep up with. This is not a metaphor. Seth Lloyd, the MIT physicist and quantum information theorist, made a version of this argument in his 2006 book Programming the Universe. Lloyd's argument at the time was a philosophical one. He argued that the universe should be understood as a quantum computer, that the physical evolution of the universe could be thought of in some abstract sense as the running of a vast quantum computation. The argument was attractive, but it was, at the time, hard to falsify or confirm. There was no specific experimental signature that distinguished the universe's quantum behavior from mere quantum mechanics, in a way that justified the quantum computer framing. The LHC magic measurement provides, for the first time, that specific signature. The universe is not merely quantum. The universe is, in the precise narrow technical sense that quantum information theorists care about, doing the kind of quantum mechanics that classical computers cannot keep up with. It is producing non-stabilizer states. It is producing them at extraordinarily high rates, in extraordinarily diverse conditions, in regimes that span from the gentlest atomic interactions to the most violent particle collisions ever measured. The universe was the first quantum computer. The universe was also, by the strictest definition, a quantum computer that always had quantum advantage. The universe has been running with the magic on continuously since the first microseconds of cosmic history. I want to sit with this, because the realization when it lands is not a comfortable one. It is not comfortable for the engineers building quantum computers because it suggests that what they are doing is not the heroic act of creating a new regime of physical possibility, but rather the more modest act of cornering a property of nature that has always been there. It is not comfortable for the physicists studying the foundations of quantum mechanics, because it suggests that the boundary between ordinary quantum mechanics and quantum computation is not a real boundary, that the universe never had two modes, one ordinary and one computational, but only the single regime that it has always been in. It is not comfortable for anyone who has been thinking of quantum computing as a new frontier, because the result implies that the frontier is not new. The frontier is just the universe. The frontier has been here all along. We are very late guests at our own party. There is, in this, something that feels almost like grief. I do not want to overstate it, because grief is too strong a word for what is, in the end, a piece of news about a property of quantum states. But there is a quiet shift in how you have to think about the relationship between human technology and the universe. When the Wright brothers built the first airplane, they were doing something that the universe had not, as far as we know, done before. There were no airplanes in the cosmos before 1903. When Einstein wrote down general relativity, he was articulating a structure that had always been there, but he was the first to write it down. The structure was new to human knowledge. When the engineers at Google built Sycamore, the first quantum processor to achieve so-called quantum supremacy in 2019, they were doing something that, in their framing, the universe had not previously done, exploiting quantum mechanical resources for computational tasks. They were creating a new use for an old physics. The LHC result complicates this last picture. The universe had already been doing what Sycamore was doing. Not just had it been doing it, but had been doing it everywhere, all the time, with no effort, since the beginning of cosmic history. The Sycamore experiment was not creating a new use for the universe's resources. It was, with great difficulty, finally building a tool that could read what the universe had been writing in its own internal language since the start. We had finally caught up, or rather, We had finally invented the first tool that could begin to catch up. The catching up is not over. The catching up will continue for a long time, but the framing of "we are pioneering a new frontier" has, in 2024, become harder to sustain. What replaces it? What is the replacement framing? I would suggest something like this. The replacement framing is that we are, very slowly, learning to listen to a universe that has been speaking in a language we did not previously have the alphabet for. The alphabet has been arriving in pieces. The first piece was the discovery of quantum mechanics in the 1920s, when we learned that the universe was not classical. The second piece was the discovery of Bell's theorem in the 1960s, when we learned that the universe was non-local. The third piece was the development of quantum information theory, starting in the 1970s and accelerating in the 1990s, when we learned that the universe was, in some operational sense, a computer. The fourth piece, the piece that is arriving right now, in our own time, in the white papers of the 2020s, is the discovery that the universe's computation is not classical grade. It is genuinely quantum grade. It is, by the strict mathematical definition, of the kind that no classical computer can match. The universe was always at a frontier that we are only now beginning to approach. I am going to bring back, here, a phrase I introduced near the beginning of this video. I said, when we first started, that the word is not a metaphor. I meant the word magic. I asked you then to hold on to that, to remember that when we used the word, we were using it in its technical sense, the formal sense, the sense it has carried in quantum information theory for almost 20 years. I want to come back to that phrase now, because we have, in the intervening time, walked through the math, the data, the experiments, the conceptual lineage, the four anomalies, the engineering question. We have seen, in detail, what the word actually refers to. And I want to repeat the phrase now, with the full weight of what it actually carries. The word is not a metaphor. The universe is, in the formal technical mathematical sense, producing the resource that quantum computer engineers are still trying to engineer. The universe is producing it everywhere, all the time, without effort, since the first hot moments of cosmic history. The word is not a metaphor. The word is exactly the word that fits. There is, I think, a particular kind of awe that comes with this realization. It is not the awe of looking up at a vast and unfamiliar landscape. It is the awe of realizing that the landscape was always familiar, and that you were the one who had not been looking. The universe was always like this. The universe was always doing this. The strange and beautiful fact is not that the universe is doing something new. The strange and beautiful fact is that we have, very recently, finally noticed. That is the picture I want you to hold. As we move into the closing of the video, the universe was always here. The universe was always at the destination. We are slowly, with great patience, catching up. Part 12. What else is hiding in plain sight? I want to close with a part of the story that I find personally the most unsettling. Not the magic itself, not the spin density matrix, not the room with the ceiling. The thing I find most unsettling about this whole story is the timing. I want to draw your attention, one more time, to the timing. The data on which Chris White and Martin White ran their calculation had been sitting on disk for years. The Atlas spin correlation measurements that they used went back to 2015. The CMS measurements went back to 2016. The mathematical formula they used, the stabilizer Rényi entropy of Lyon, Oliviero, and Hammer, had been published in 2022. The conceptual framework of magic as a quantum resource had been around since 2005. There was, in 2023, no technical barrier whatsoever to running this calculation. The data was open, the formula was open, the conceptual framework was open. The calculation, by the author's own admission, took about an afternoon. And yet, until September of 2024, no one had done it. This is not a story about a breakthrough that required new instruments, or new theory, or new data. This is a story about a question that no one thought to ask, until two physicists, half a world apart, with the same last name, finally asked it. The result was always there. The result was always implied by the equations. The result was always present in the data. The only thing missing was the question. And the question, when it finally arrived, was small. It was the kind of question that any sufficiently interdisciplinary graduate student could have asked at any point in the last 2 years. It is just that, until 2024, no sufficiently interdisciplinary graduate student happened to be in the room. This is what I find unsettling. Not the result itself, although the result is extraordinary, but the implication that the universe is full of similar results, just sitting there, waiting for the right question. The toolkit of quantum information theory is rich. We have talked, in this video, about one of its tools, the stabilizer Renyi entropy, the magic measure. But there are others. There is the geometric measure of entanglement. There is the relative entropy of coherence. There is the quantum Fisher information. There is the discord, the squashed entanglement, the entanglement of formation. Each of these is a measure of some specific quantum resource. Each of them is, in principle, computable from data that experimentalists in various fields are already collecting. Each of them has, in all likelihood, never been computed on the data of any particle physics experiment, or any condensed matter experiment, or any atomic physics experiment that did not specifically have that measurement as its goal. How many of those quantities, if you computed them on data we already have, would come back with surprising, structured, physically meaningful values? How many fundamental properties of the universe are hiding in plain sight, in published plots, in old papers, in archived data, waiting for somebody to point a new mathematical instrument at them? The honest answer, I think, is that we do not know. And the honest answer also is, probably many of them. The LHC magic result is not a one-off. It is, I think, the first instance of a kind of result we're going to see more of in the coming years. Results that emerge not from new data, but from old data, processed through new lenses, by people who bring tools from one field into another. This is, when you think about it, a strange way to do science. We tend to assume that the way you discover new things about the universe is to build a bigger telescope, or a faster accelerator, or a more sensitive detector, and then you point the new instrument at something, and you see what nobody has seen before, and that is certainly one of the ways. But the LHC magic result is a different way. It is the discovery, in the existing data, of something that the existing data had always contained, but that nobody had asked the existing data to reveal. The discovery is not at the frontier of measurement. The discovery is at the frontier of interpretation. The frontier of interpretation is, in some sense, more accessible than the frontier of measurement. Anyone with a good idea and an afternoon can, in principle, explore it. But it is also, in another sense, harder, because the good idea is not something you can plan to have. The good idea has to come from the right collision of two specialties at the right moment, and the conditions for that collision are not something you can engineer. I started this video by saying that the result we are walking through is the kind of result you remember. I want to come back to that and refine it. The result is the kind of result that, in 5 years, 10 years, 20 years, will be told differently from how we are telling it now. Right now, the result is fresh. It is a measurement. It is a paper at a conference. It is a number, non-zero, magic-rich top-quark spin density matrices that the field has just absorbed and is starting to think about. In 5 years, it will probably be in textbooks. In 10 years, it will probably be one of those facts that every graduate student in particle physics or quantum information learns as part of their basic training. In 20 years, the field will probably look back at 2024 as the year that the conceptual fence between particle physics and quantum information came down, and as the year that the universe as quantum computer thesis stopped being a philosophical position and started being a measured property of nature. But right now, we are early. We are still in the months and years after the conference. The implications are still landing, and what I want to leave you with, in these last few minutes, is the sense that the implications are not going to stop landing. The result that Chris White and Martin White announced in St. Malo will almost certainly be followed by a series of similar results, calculations applied to other particle systems, to condensed matter systems, to atomic physics, possibly even to biological systems, where the existing data is processed through the magic formula, and where the magic in many cases will turn out to be measurably non-zero. Each of those results will be a small extension of the LHC result. Each of them will add another tile to the mosaic of the realization that magic is everywhere in nature. And the mosaic, when it is complete, many years from now, decades from now, possibly long after any of us are still around to see it, will form a picture of the universe that we're only just beginning to be able to see. I want to close with the phrase one more time. The phrase which I have been threading through this whole video is, "It was there. It is gone. It will be back." I have, until now, been using that phrase to describe top quarks, the fleeting existence of a magic-rich quantum state in a proton-proton collision, the brevity of its life, the recurrence of its production in the next bunch crossing 25 nanoseconds later. But I want to apply the phrase now, in closing, to the result itself, and to the kind of result it represents. The result was there, in the data, for years, before anyone noticed. It is now in the published literature, processed, understood, becoming part of the standard knowledge of two fields, and it will be back, not as the same result, but as the next result, and the result after that, and the result after that, as the larger program of porting quantum information theory into the rest of physics continues to unfold. There will be many such results. We are going to see them, one at a time, over the coming years. Each one will be small. Each one will be, in some specific way, surprising. And taken together, they will reshape, slowly, our picture of what kind of universe we are living in. The universe is a quantum computer, in the strict technical sense. The universe has always been running. The universe has always been ahead of us. And we are, very slowly, with great patience and a few good ideas, learning to read what the universe was writing all along. It is past time to settle in. The lights are dim. The cosmos is quiet. The proton beams are off for now, in the LHC tunnel 100 meters below the French countryside. They will start again, soon. The magic will start again, soon. The universe will keep doing what it has always done, and we, in the meantime, will keep doing what we have just started to learn how to do, which is to listen. That is where I will leave you tonight. With the picture of an empty field, with the picture of a quiet sky, with the knowledge that in every cubic millimeter of the air around you, and in every interaction between every particle in every star you can see, the universe is doing the thing that the engineers at the LHC just learned to measure for the first time. The universe is producing magic. The universe was always producing magic. The universe does not need us to notice. And yet, in this moment, in 2026, we have noticed. Quietly. Just barely. With the help of two physicists who shared a name and a 6-line calculation and an afternoon's worth of curiosity, it is enough to know